Thank you very much, everyone, for joining, and I hope you are all well. As Elizabeth said, I'm Taylor Nicholls at exactEarth here in Canada. We are a leader in ship tracking. We offer the largest satellite AIS constellation and the first global persistent real-time AIS service in the world. As mentioned, alongside myself, we have Eric Nallon from our strategic partners, CCRi. So thank you for joining on, Eric. Today we're going to talk about our approach for building a data-driven maritime port boundary layer and why having a port boundary layer helps while exploring maritime behaviors and activities. So with our AIS service, we can track ships anywhere in the world. But for today's session, we're going to focus on port movements, when ships arrive and when they depart. But getting to that point obviously requires having an accurate and reliable port boundary layer. So there's two examples here we wanted to show. On the left side, bottom left, we have a global view of all the port arrivals and departures. On the right side, we have an aggregated view of a 24-hour heat map showing the port of Hong Kong. Next slide. So with the data, we can solve some really interesting problems. One example would be COVID-19 impacts. But that requires an accurate understanding of exactly when and where ships contact land. The example here is the Port of Long Beach in Southern California. The diagram on the top right from 2019 shows a pretty consistent pattern. However, we can notice a very stark reduction towards the end of February 2020, when the effects of COVID-19 worldwide were felt for sure. Next slide. So at this point, I will turn it over to Eric, who will start talking about similar trends and effects in New York City, but then get into the methodology to solve this data-driven definition of port boundary layers that are so critical for evaluating maritime behaviors and activities.
Okay, thanks, Taylor, for that intro. As you mentioned, I'm gonna have a few slides here. I'm going to go over some examples and broadly the techniques that we use to create the port boundary layer, and then also some other maritime products that can be created on top of this port boundary layer and really rely on that port boundary layer. And then I'm going to make sure I reserve some time because I have a live demo at the end that I'd like to pull up the map and pan around, look at some of the ports and some of the live AIS, and we can inspect some of the ports. So as Taylor mentioned, so this is an example of, on the left-hand side, is a port boundary layer that was created around New York City using our clustering techniques and is also showing a heat map of 1 week arrivals for vessels. And that's the red that you see there in the heat map, and you can see the port boundary. Then you could start doing fairly basic but interesting things. For instance, on the right-hand side, there's an animated GIF. So this is daily aggregated vessel types on an hourly in an hourly bin, and then they're divided up into different vessel types. And some of the things that you can start seeing are different trends that kind of pop out. So, for instance, that the top line plot there is all vessels. So that's every vessel type. And you can see that there's some obvious things that kind of stick out. In the middle, there's two humps that are kind of lower than the rest. And that's the weekend, which isn't too surprising. But also during the week, you could see that there's kind of an intraday fluctuation. But if you actually look at the different vessel types, you can see that that's actually completely dominated from the fishing vessels that cause that kind of pattern to appear. So this is just kind of an example I wanted to show of something that could be done at a global scale. So this is one port, but this is something that could just be done every day, updated on a schedule for every port in the world as we track arrivals and departures. So what is the motivation behind this? Sometimes it's not clear because if you're not really in this space, you wouldn't really know this. The most widely accepted port layer at the moment that's publicly available is the World Port Index. There are a few others, but that is a very popular one. And These only provide a point geometry, so a lat and a long, and that's it. There are some providers out there that do have some port layers that might be similar to what we're going to describe today. Many times they're made manually, which is extremely tedious. And the problem is they don't evolve. The process that we're describing is a data-driven approach, so something that could be run on a schedule at a daily, weekly, monthly interval. And it's data-driven and it's adaptable, so it evolves with time. So if it evolves with time, it evolves with changing patterns around ports. Maybe new things get built, vessels are operating in different ways. You can start to capture that shape over time. So what I wanted to also point out is this is really foundational for creating analytics and different maritime products on top of this. The geometry is just an enabler, and the AIS is necessary to get there. But this starts enabling things like just port statistics, what types of vessels are in a certain port, what countries visit that port, all different kinds of statistical trends. And then you could think that in reality, really just creating our own machine learning model training data. So you can start doing anomaly detection, look for vessels that are entering ports that have a very different physical size or some vessel attribute that is anomalous. So you could start detecting outliers in real time. Time series forecasting, so we could start making forecast models to forecast volumes of certain types of ship in the future. We could also start to think about predicting unknown vessel attributes when there may be missing data from records. So I'm going to briefly go over the approach. I'd love to answer more in-depth questions later on or after this presentation. So the data that we used for this was provided by exactEarth. It was a 1.5 year worldwide AIS. We applied some kinematic filtering to get vessels that are either slow moving or stopped. And then this really resulted in a fairly large data set, still about 160 gigabytes, over 800 million records. So this is quite a bit of data. And for these specific clustering algorithms, you usually need to pull all of this into memory. So one of the important things about how this process works is we use something called, I call it a seed layer, but it's really a starting layer that we're going to basically design this off of. And the World Port Index is what is used here, but the process is easily adaptable to another port layer or aggregating multiple port layers together. So we stood up a distributed compute environment, AWS EC2 instance with lots of RAM. We had to do some parallelization, or else this probably would have taken a very long time. We were able to get it to finish in just a couple hours. So the algorithm approach here is it's an unsupervised density-based spatial clustering DB scan. It's pretty widely known and used for quite a long time. It's a good application for this right now. And we did some additional things that we had to deal with, such as splitting up polygons. So the next couple of slides, I'm just going to show some images, and then I'm going to jump into a demo, and we could look at a few things live. So really what I'm showing here is we're taking AIS, and now we're creating the port boundaries. And here's just an example of a few boundaries and how they're split up. And I also have some AIS moored vessels that were moving slow, and you can see how they kind of reside inside of those polygons. So these were autonomously created, and through that process I described, and you could see that the World Port Index is the kind of faint yellow circular dot that's inside each one of those polygons, and that was used as the kind of the foundation layer. So as I'm stating here is that the AIS is foundational to port boundaries, as these boundaries are foundational for anything further. So this is kind of just the start to kind of bigger and more complex things. Another thing that we had worked on that was enabled by the port boundaries was to make vessel routes. So we created a global vessel route network, a maritime superhighway, if you will. And each one of these routes has a start and end port. So it's delimited on each end by a port. So if we know where a vessel is going, we could start to think about even more interesting things like what is the vessel's next port and how long will it take to get there. So that leads to my last slide before I go into the demo of a next port, and an ETA prediction. So now that we have this global network of vessel routes, we could most easily use the reported destination from AIS if provided, and find the port, find the vessel route. And we trained a machine learning model on a pre-trained model to do ETA prediction. And in this example, I'm showing on the top, that top GIF there, the red line is the vessel route that was selected for this particular vessel, given the vessel's reported destination. And then we took its current position and speed, and we used our pre-trained machine learning model to do a ETA prediction. And you could see, actually playing this over time, once we had the history for this vessel, you could see how well it travels along that particular route. And then the right-hand side, you could see that the starting and ending ports where that vessel route begins and ends. So this was a really neat kind of ending to see this progress all the way from raw AIS observations into an ETA prediction on a route. It's a very fun process to go through. So at this point, I'm going to transition over to a demo here. So I have a world view here. I'm going to bring up, this is the World Port Index. So this is a global ports. I think there's about 3,600 ports. Now I'm going to bring up our port boundary layer that's in blue, and I'll leave the World Port Index for now, but I'll probably turn it off at some point. So I'm going to zoom in to the Mediterranean here, and I'll start clicking around a little bit. So here's around Venice, and here is an example of one of the port layers. You can zoom in, you can see here's the World Port Index point. So if you were using the World Port Index, this is all you would have, is that point. But using data over a long period of time and these clustering techniques, we can start to figure out where vessels really stop for that particular port. I'll also just open up a few here, and I'll start panning around to different parts of the world so you can see the different shapes. If you're familiar with the World Port Index, there's many attributes in their field. So I'm kind of just pulling the most popular ones forward. Another thing that we've done, which was really important, was to associate the UN low code with the port, because that is used very often. I was extremely surprised to find that the World Port Index does not actually have the World Port or the UN low code associated with each port. So before I show you a few more things, I'd like to just kind of pan around to different parts of the world, and you could see the different polygons that were created for the different ports. I'm going to go over to Hong Kong. That's always a pretty busy area. I also have loaded here on the left-hand side, there's a lot of things I have here. I have live AIS. This is exactEarth's AIS coming in live. And I have two filters put in here, one for kind of low speed stopped, and then one for moving. So if I turn on that, these are anchored vessels that are moving slowly. You could see quite a few of them captured in these boundaries. You could also see quite a few of them not captured in any boundary, and that's because the World Port Index does not have a port location for some of those areas. But using a different port layer, either supplementing the World Port Index with new ports, would give you those other ports that aren't available there. Here's a couple more examples of some more complex shapes that we created, and you can see some of the vessels inside there. So one of the things I want to end with is I'm going to go back to the Mediterranean, because I have some historical AIS loaded, and I also want to show you the vessel routes that get created from the different boundaries. So here's the Mediterranean. It has a very complex network. These are color coded by vessel type. And if I turned on moving AIS, you could see all the different routes that these vessels take. So lastly, I'll show you, I've preloaded historical AIS here. It's about 1.7 million observations over just about a day. I'm going to play those just over time, so you could start to see how they travel along those routes. And just remember, those routes were created from the ports, and the ports from the AIS. This is really kind of foundational. So you could, if you look at this network, you could just see them traveling, you know, in all these different maritime routes, especially in this area. It's very dense and busy.